Hello there. Did you know that every cell of your body comprises of sodium chloride? Yet, elemental sodium is known to be extremely flammable and also is prone to explosion, while the chlorine gas is a poisonous gas which is lethal when taken by a person. But why does the sodium chloride is not poisonous for us? Can I say it is ironic? Or shall I say it is ionic, isn't it? When the sodium and chloride is combined to form a single compound known as sodium chloride, it is not poisonous anymore because they are electrically charged, and these electrically charged particles are called as ions. The sodium has a positive charge, while the other, the chlorine ion, is negatively charged. They finally attract to each other, and these brazen elements finally met each other's match. Hello, my name is Mika Angela Picador, and for today's video, I am gonna show you on how I made the 3D prototype of the sodium chloride crystal structure. I use sodium chloride because it is the most commonly used compound, and it is also easy to relate with. But of course, before we start, let us know more about the physical structure of the compound. Sodium chloride crystal is made up of an anion and a cation. Since it is ionically bonded to each other, so the sodium is the one that possesses the cation, while the chloride ion is possessed by the anion. With a formula unit of NaCl-, sodium chloride crystal is a face-centered cubic closed-packed structure. The chloride ions, being comparatively larger, occupied the corner and face-centered positions. The sodium ions, on the other hand, being smaller in size, goes filling the voids. Thus, sodium ions occupy the octahedral voids in a cubic closed structure. Chlorine ions are face-centered and are located at the corners, while sodium ions, they are located at the mid-edges, or the spaces between the larger chlorine ions. On extending the structure, we will see that each chloride ion is surrounded by 6 sodium ions, while each sodium ion is surrounded by 6 chloride ions, so the coordination number is 6. Now, let us calculate the total number of ions inside a single unit cell. Now, let us calculate the total number of ions per unit cell. The total number of chloride ions per unit cell is equal to the sum of chloride ions at corners and face centers. The total number of chloride ions is equal to 8 corners by 1/8 corners plus 6 faces by 1/2 per face, which is equal to 4. Total number of sodium ions per unit cell is equal to the sum of sodium ions on the 12 edges and 1 at the center of the cube. Total number of sodium ions is equal to 12 corners by 1/4 per edge plus 1 ion in the center, which is equal to 4. Thus, the unit cell of any sodium chloride contains 4 chloride ions and 4 sodium ions. The chloride ions with a radius of 1.81 angstroms are larger than the sodium ion with a radius of 0.95 angstrom. Its structure is an octahedron. So now, we have here a simple 3D model of our sodium chloride compound structure. This form is based from the literature source from chemguide.co. Well, there are main steps before we can proceed. The first step is to locate the mid-edges. So, there are 4 edges at the top, and as well as the 4 edges at the bottom, and 4 edges at the vertical side of this cube. Now, we will go on to locate the positions of sodium, which is possessed by the red color, and the chloride ions, which is possessed by the yellow color. If I take the chlorine ion and start, the chlorine ion is 0, 0, 0, 1/2, 1/2, 0, 1/2, 0, 1/2, and 0, 1/2, 1/2. While for sodium ions, the position of it is easy to locate since we already knew the positions of chloride ions. The positions are 1/2, 1/2, 1/2, 0, 0, 1/2, 0, 1/2, 0, 1/2, 0, 0. Next up is packing density and packing structure. Packing density is the ratio of the volume of a single unit cell or atom inside the unit cell to the volume of the whole unit cell. As you can see, these are the unit cell characteristics of a face-centered cubic structure. For its cube edge length, which is A, is equal to 2 by R by the square root of 2. Next, and the number of atoms per unit cell is equal to 4, which we have calculated earlier. Its coordination number is 12, while its APF or the packing fraction is 0.74. It is also important to note that each corner of atom touches the atom in the centers of the 3 adjacent faces, but corner atoms do not touch other corner atoms. In the FCC unit cell, there are 6 atoms on the cube surfaces, but only with 1/2 of their sphere volume, or in total 3 whole atomic volumes. In addition, there are 8 other atoms on the cube corner, but only with 1/8 each, which in whole is equivalent to 1 whole atomic volume. In the total, the volume of 4 atomic spheres is in the unit cell with the atomic volume V sub A. So, in getting the atomic volume, it is represented by the following equation. V sub A is equal to 4 times the volume of the sphere, which is equal to 4/3 pi times the cubic of the radius. Then, it is equal to 16/3 times pi multiplied by the open quantity square root of 2 over 4 multiplied by A closed quantity to the power of 3. So, the volume of the sphere is equal to square root of 2 over 6 pi multiplied by the cubic of the A. This atomic volume, V sub A, can now put into relation to the unit cell volume, which is V sub U is equal to the cubic of A. The packing density, or PD, of the face-centered cubic grid is calculated as follows. The PD is the ratio of the atomic volume to the unit cell volume. So it is equal to the square root of 2 over 6 pi times the cubic of A over the cubic of A, which is simply equal to the square root of 2 over 6 pi, which is approximately equals to 0.74. As depicted in the literature from the ChemGuide.co, a small representative of a sodium chloride lattice looks like this. Only those ions joined by lines are actually touching each other. The sodium ion in the center is being touched by 6 chloride ions. By chance, we might just as well have centered the diagram around a chloride ion. That, of course, would be touched by 6 sodium ions. Sodium chloride has high melting and boiling points since most of the ionic compounds possess a high melting and boiling points. Sodium chloride is highly soluble in water due to the positive ions that are attracted to the lone pairs on water molecules and covalent bonds may form. Sodium chloride is insoluble to organic solvents. This is also typically characteristic of ionic compounds like sodium chloride, since the attractions between the solvents and the ions are not big enough to overcome the attractions holding up the chloride. Sodium chloride in its solid form is not conductive to electricity. Sodium chloride is an essential nutrient and is used in healthcare to prevent patients from becoming dehydrated. It is used as a food preservative as well and as a seasoning to enhance flavor. Sodium chloride is also used in manufacturing to make plastics and other products. It is also used to de-ice roads and sidewalks. So in the process of making the 3D crystal structure, this is the flow diagram that is being observed all throughout the activity. So the input would be the modeling clay, which is processed through the molding, and as the end result, it is formed as a 3D model for the sodium chloride. These are the following procedures and the actual process of constructing the 3D model. A need to emphasize the connections between the atoms inside a unit cell so that I could able to represent a clear exhibition of this 3D model. We create a 3D model to preserve structure of a particle, which in this case is the sodium chloride. This will be another level of understanding. Then, by just sitting along reading the definitions of it, it may be exposed to the different calculations and hence are proved by simulating the physical structure of the crystal lattice. So, of a solid encourages me to delve more into the lesson one. So, for my recommendation, there was certainly a limitation related to the understanding and how the model works in reality, and that is why theories, principles, and other useful calculations must be completely and explicitly incorporated in the presentation of the model.